Good evening, everyone. On behalf of IEEE ADSF SIGHT, it's my privilege to extend a warm welcome to each and every one of you to our weekly interaction program. As we gather here today, after a true interaction program held the past 2 weeks, we embark on a journey of exploration and discovery into the realm of sustainable energy. I also extend a warm welcome to our chief guest, Mr. Sivaraman Pete, senior member of IEEE, give a technical talk on electrical vehicle charging infrastructure. Welcome, sir.
Hi Harsini, thank you. Thanks for your introduction. I am once again welcoming everyone to the IEEE ADSF site, the interaction program on solar energy. So the first two sessions is completed in the previous 2 weeks. Today is the third session. So in this session, I am welcoming you all, and I hope and I have covered in that previous two sessions. I have covered the basis of solar energy. So how much potential we have in our India. Then we have gone through the various solar energy harnessing technology. Then rooftop solar PV system. In the last week, I have take you to the micro inverter application for solar PV system. Yeah, so in this session, I will give some uh, light about the rooftop solar PV system. So it is the continuation of the previous two sessions, especially this solar rooftop solar PV system. It is the continuation of the last two sessions. So if you have any doubt in the previous two sessions, you can turn on the mic, and you can ask your questions, or else we can directly go to this today's session. Yeah, so I will continue with today's session. So in the last session, we have seen that a micro inverter and a string inverter used for the rooftop based applications. I told that string inverter, we need to frame the stringing. So stringing means it is a series and parallel connection of multiple solar PV panels. So in this figure, you can able to see, sorry. So in this figure, you can able to see the typical solar PV module series connection, and in the right side, you can able to see the typical uh, solar PV modules in the parallel connection. So this is the string inverter. So string inverter having a number of MPPTs. So MPPTs are called as maximum power point tracking. I will explain in this presentation. So in this photograph, it is the string inverter of 250 kilowatt. So this inverter having almost 12 number of MPPTs. So it means 12 number of stringing we have to form to cater or to extract the maximum power of 250 kilowatt for this particular inverter. So this is the typical one. So this is the string inverter of SMA make, and so this is the display. So I hope you remember that this is the 20 kilowatt inverter. So on the last session itself, I told that solar inverters ratings are in kVA rating only, not in kilowatt rating. So if someone is saying it is in kilowatt rating, so it means it is operating at unity power factor. So you should always remember these things. Inverter ratings are not in kilowatt, it will be in kVA. So if you come across the word kilowatt solar inverter rating in kilowatt, so it means that it is in unity power factor condition. So solar inverters can able to operate plus or minus 0.88 power factor. It means it can able to operate 0.8 power factor lagging as well as 0.8 power factor leading. So whenever you change the power factor from unity to 0.8 or in between any value, so kilowatt is not equal to kVA, right? So this is the one fundamental thing you have to always keep in mind. Okay, so when I have taken this photo, that time this 20 kilowatt inverter is producing almost 3468 watts. So it means 3.4 kilowatt it is generating at that time, and the particular day it has delivered almost 50.68 kilowatt hour, so equal to 50.68 unit. So still till the installation it's generated almost 123 megawatt hour of unit. So this is the inverter, solar string inverter. Then this will be the DC-DB. DC-DB. So it means DC current distribution board. So here MCB will be there. This will be MCB. Then here this one is the SPD. SPD means surge protective device. Okay. So going to that, this is the comparison of string and micro inverter. I'm not touching that. So I will start the today's session from here. Stringing layout. So this is the inverter actually. This will be the inverter. Up to this part, this will be the DC part. So here they mentioned DC. This will be the DC part. Okay. So from this onwards, this will be the AC side. Okay. So you remember I told that in solar PV system we have two DC voltage. One is 1000 volt for string inverter for rooftop based application. Another one is 1500 volt for string inverter for utility scale application, as well as the central inverter that will operate in 1500 volt, and string inverter for rooftop application alone that will operate in 1000 volt. Okay. So in this inverter, this will be our fuse box. So here they splitted that DCDB into two box. This will be the fuse box, and this will be the isolator box. So isolator means establishing the connection or disconnecting the connection between the inverter to the solar PV panel. So that is called as isolator. So that we can achieve by using MCCB also. Suppose if we are using the fuse, then isolator is mandatory. Suppose if we are using the MCB, then isolator is not required. By making the on and off of MCB, we can able to isolate the solar PV panel from the inverter. Suppose if you are using the fuse, then isolator is mandatory. So in most of the applications, fuse and isolator as well as the same time MCB, both are employed, right? So it is up to you, the designer who is designing, whether needs to go with fuse and with isolator or can go with the MCB. Okay, so here this inverter having two MPPTs. Okay, so the number of MPPT is 2. So this portion will be connected to MPPT1, and this part will be connected to MPPT2. Okay, so if the number of MPPT is 3, number of MPPT is 3, then similar to this one, we have to include one more connection that needs to go to this inverter. So this will be 3. So it means that how many number of MPPTs we have. So those many number of stringing we have to frame. So how we need to frame that I will explain in the upcoming slide. I hope now you can able to understand what is mean by stringing. So stringing is the series and parallel combination. In this photograph, you can able to see only uh, the number of panels connected in series, right? So moving further, this is the nameplate rating of one string inverter, uh, single phase 230 volt, single phase 230 volt. Its power rating is 3.9 kilowatt, 3.9 kilowatt. Okay, so this is the rating of this inverter. So its maximum voltage is 550 and its MPPT voltage is 700, sorry, 70 to 500 volt. So this is the MPPT voltage. Okay, so and it's in the DC side, the maximum voltage is 550. The MPPT voltage is 70 to 500, and maximum input current 13 ampere DC, and maximum, this is MPPT current, MPPT current, and this will be short circuit current. ISC means short circuit. Short circuits are generally called as ISSC. So ISC means short circuit current. So that current is 19.5 ampere. So in the AC side, it is a single phase 230 volt AC, 50 hertz frequency absolutely. Based on the country hertz, it is 50 hertz. Then maximum AC current is 50, sorry, 17 ampere, and its power factor in most of the time it can able to operate 0.99, greater than 0.99, so we can say as unity. So most of the inverter, as I told, it can able to operate plus or minus 0.8 power factor, it can able to operate. Okay, so this is the nameplate details of a typical string inverter, right? Suppose if you want to design a string inverter for your rooftop based application, first thing you have to you have to do that is you have to freeze what string inverter you are going to use, then what solar PV panel we are going to use, you are going to use. So these two are mandatory for design the system. Okay, so moving further, this is the nameplate detail. The left one is the nameplate detail of a 300-watt solar inverter. 300-watt solar inverter. Its nameplate details are given here. So P max is the maximum power 300 watt, and VOC is the open circuit voltage, that is 46.265 volt, and the short circuit current is 8.576 ampere. Then maximum power voltage, that is VMP, that is 7.052, and maximum power current IMP, it's 8.082 ampere, right? So in the right side, and you can able to see this is the curve of the solar PV panel. So this curve is called as IV curve. I means current, V is voltage. So plotting the characteristics of the panel with respect to voltage and current, that is called as IV curve. In the second one, this blue curve is called as PV curve. So this curve is plotting the characteristics of voltage with respect to power. So here the IV curve x-axis will be current, I in PV, sorry, y-axis is current, x-axis is voltage. In PV curve, x-axis is voltage again. In y-axis, it will be power P. Okay, so now we have to populate the nameplate values here. So here you can able to see the P max is 300 watt. So this point is called as P max, that is 300 watt. 300 watt. This is the maximum power point of the particular solar PV panel. Then open circuit voltage VOC, that is 46.265. This is the VOC point, 46.265 volt. Then VMP is 37.052. 37.052 voltage. Upon the current short circuit current IAC is this point is uh, 8.576, and IMP is 8.082. So if you plot the nameplate details into the IV curve and PV curve, sorry, this is the P max point. So if you plot the nameplate details into this IV curve and PV curve, you have to populate like this. Okay. So in the IV curve, the maximum point will occur at this point. So this point is called as P max, or maximum power point. In PV curve, if you see, this is the point. Okay, in this point only maximum power occur. In simple words, so we can able to say the maximum power point occur wherever the IMP, the maximum power point current, and the VMP, the maximum power voltage, where it is getting intersection, that point is called as maximum power point. So that is 300 watt, right? So I'm explaining these things in a slow manner so that everyone can able to understand. If you have any doubt, you can unmute yourself and you can ask the question, because this is the very much important to design any solar PV system. If you have any doubt, Darshini?
No, sir.
Okay, Hemachandran?
No, sir.
Okay, fine. Moving further, we have seen that the inverters. Now what I will do, I will design this yeah, rooftop solar PV system for this 3.9 kilowatt inverter. Okay, so the total rating is 3.9 kilowatt. Okay, so we are having the solar panel. This will be the inverter rating. Then we are having 300 watt solar panel. So 300 watt means 300 watt peak is the maximum. Okay. So first we have to calculate number of panels, NOP. So we have to calculate based on this power rating of the inverter. So that is 3900 divided by 300. So how much it will come? 3900 divided by 300. this will be 13. This will be 13. So we need the number of panel which is minimum of 13. So we need minimum number of panel is 13. Okay. So here I would like to explain one point that is called as AC versus DC ratio. So here there are some ratio called 1 is to 1, 1 is to 1.5. So like that, there are some AC versus DC ratio is there. So what it means for 3.9 kilowatt of for AC system, in 1 is to 1 ratio means, so our solar panel also 3.9 kilowatt only. For an example, 1.5 DC ratio. So, so we have to multiply 3.9 multiplied by 1.5. So this will be equal to multiplied by 1.5 equal to 5.85 kilowatt of panel we have to install. So that is the meaning of AC versus DC ratio. So why this ratio is important means especially in terms of energy production from the solar PV plant. Suppose if you plot the uh, 24 hours load profile, sorry, generation profile of the solar PV system. So this point is 0 and this is the 24 hours. This will be in hours. So the solar will start the solar characteristics will be like this curve. This will be 6 o'clock in the morning. This will be 6 o'clock in the evening. Okay, so you can able to have some higher amount of power between 10 o'clock in the morning to 3 o'clock in the evening. So in between this only we can able to have some higher power. So morning 6 to 9 and evening 3 to 6 we are getting the lower power only. This will be the power P. Suppose we suppose if the inverters are operating at this point. So when the inverter operating at this time period, morning 6 to 10, it will not give the rated output power. Suppose here in this example we seen, right, it is 3.9 kilowatt. So when inverter is operating at this region, that time only it will give 3.9 kilowatt. Suppose if it is operating in this region, then it will not be 3.9 kilowatt. This will be less value of 3.9 kilowatt. Okay, so in order to have or in order to achieve the higher amount of energy from the solar PV system, we have to go with higher AC versus DC ratio. So these kind of systems are more commonly used in utility scale solar PV plant, where this plant is especially connected to the power grid and only the purpose only for generating the power exporting to the grid. So those kind of plants we are using higher AC versus DC ratio. Okay, so in this example, I will consider only 1 is to 1 AC versus DC ratio. So based on that, we need minimum of 13 number of solar PV panels. Okay, so the number of solar PV panels is NOP equal to 13. So it means we are going to have 13 number of solar PV panel minimum in our system. Okay, so and also the next what we have to do, we have to match the MPPT voltage of the inverter to the MPPT voltage of the solar PV module. So here our MPPT voltage is 37.502. So panel PMP is equal to 37 volt. So simply, okay. So when we are having 30 number of panels, so those 30 number of panels has to comes under this MPPT voltage range. Okay. So for that, what we have to do, we have to calculate the VMP VMP inverter VMP. So 37 multiplied by 13. So 37 multiplied by 13 is equal to 481 volt. Okay, 481 volt. So this is the voltage when we are connecting all the 13 inverters. 13 inverters. So this will be the 13 panels. So this will be panel 1. This will be panel 13. So here we are having only one MPPT. If number of MPPT is not specified in this nameplate, it means it having only one MPPT. So we are connecting all the 13 modules in series, and we will connect this to the inverter. This will be inverter. This will be panel 1 to 13. Okay, so this will be series connection. After adding all the 13 modules, the VMP of the panel is 481 volt. That volts has to be comes under this 570 to 500 volt rating, MPPT voltage rating of the inverter. Okay, so that is the first point. First point, what is that? MPPT voltage of the panel has to comes within the range of MPPT voltage of the inverter. Suppose if it is coming in place of 481, if it is coming 581 means the selected number of panels in series, it's not matching. This is not a correct. This is not correct. So we have to, in order to match this number of panels with this MPPT voltage range, we have to reduce the number of panels from 581 voltage to within this 500 volt of maximum. Then second step, what we have to do, that is open circuit voltage 46 volt here. So second step, what we have to do, VOC equal to 46 volt. So 46 volt multiplied by 37, 13. 46 multiplied by 13 number of panels. So we will get 598. So we will get 598 volt. Okay. So 598 volt is the second one. Okay. So the second one is not much important, but the first one, the MPPT voltage, is most important. Okay. Then third one, maximum PV input current. So this inverter can able to operate 13 ampere of DC maximum. So here the maximum current is MPPT current is 8.082 ampere. So it is well within 13 ampere. Okay. So this condition also fine. Suppose this inverter maximum current is 13 ampere, but this current is 14 ampere means this is not a correct selection. So in that case, what we have to do? We have to change the module solar PV panel what or make, or we have to change the inverter to the different model or different make to match this. Okay, so as you all know that when we are making the number of PV panel in series, that time the voltage will get added, current will be in parallel, current will be remain same, sorry. When you are adding the solar PV panel in series, voltage will get added, current remains same. So only that 37 of VMP of panel become 481 when we added 13 number of panels in series. Okay, so here the current is remain same, that is 8 ampere, 8 ampere only. So in this circuit, if we measure the voltage between this last panel to this one, positive versus negative, this will be 481 volt. If you measure the current in this circuit, this will be 8 ampere only. Okay. Okay, so this is the case for the 1 MPPT string inverter. Okay, suppose here 2 MPPT is there, means in that case what we have to do similar to this. So this is the string. So here the number of string is 1. So uh, we have designed the number of string as 1 only. Suppose if we have two number of MPPT in the inverter, similar to this, we have to make one more string. That string is called as number 2, that has to go to the inverter. Okay, so this is the general design philosophy of the string inverter. So first one is the MPPT voltage, second one is the open circuit voltage, then third one is the MPPT current, right? So this is the general philosophy. Okay, if you have any doubt, you can please ask. If you don't have any doubt, I will move further. The connection of solar PV panel. Okay, so this will be one panel. This will be the other panel. So so in this figure, you can able to see totally five number of panels. So all these 5 panels are connected in series. Okay, so the first panel positive is connected to second panel negative. Second panel positive is connected to third panel negative. So similarly, it connected all the 5 panels and the total positive and total negative. Okay. So as I explained earlier, so when we are adding the number of panels in series, voltage will get added. So V total equal to V1 plus V2 plus up to V5 here in this example. I is remain same. So all the panels, so in this panel, this is 9 ampere. All the panels are 9 ampere. So I again remain 9 ampere as I told. Okay, so this is called as a typical solar PV panel connection. Suppose will be suppose if you are having 2 MPPT, so like this will be the string 1. Similar to that, one more string we have to establish, and that we have to connect to do the inverter. So this output will goes here. So this will be string 1. This will be string 2. So this will be connected to MPPT1 of the inverter. This will be connected to MPPT2 of the inverter. Then this side will be AC output. This is the DC part. If you see, like in this example, up to this part will be these are all the DC part and these are all the AC part, right? So similar to that. Okay, if the number of MPPT is 2 or 3 or 4, so what we have to do for the string design, if number of MPPT in the inverter is 3 means, so we have to frame the we have to frame the number of string as 3. So each string we have to connect it to the each MPPT of the inverter. So the inverter with the MPPT 1, 2, 3 means, so all the 3 strings needs to connect to each MPPT. So how then you may have the question, how we can decide the number of panels in series or number of panels in parallel, right? So for that, each string, this is the string 1, 2, 3. So each string must to follow the concept I explained here. So here the plant capacity is 3.9 kilowatt. So here for the number of panels we have considered 3.9. Okay. Suppose if it is 10 kilowatt inverter, for an example, you assume 9 kilowatt inverter for simplicity, 9 kilowatt inverter. So it having 3 MPPT, 3 MPPT. So it means each MPPT rating is 3 kilowatt. Okay. So for calculating the number of panels, this will become 3 kilowatt. So you have to design the stringing for 3 kilowatt. Okay, so it means the first string will be the number of panels for the first string is based on the 3 kilowatt. Second also for 3 kilowatt. Third also for 3 kilowatt. So that is 3000 watt I'm writing here. So put together all the 3 kilowatt will become 9 kilowatt system. So the 9 kilowatt we are connecting all the three we are taking from all the 3 strings. So connecting to the inverter. I hope everyone is clear on this, right? So moving further about the connection. So this is in this photo what you are seeing, this is the device for connecting the number of panels. Okay, this connector is called as MC4 connector. These connectors are normally called as Y connector because this look like Y, letter Y, right? So in a simple terminology, normally we will call this type of connectors are called as Y connector. This connector, the left one is called as MC4 connector. Okay, so this is the removable type. By pressing these two, we can able to disconnect this connector. Okay, so this connector is used at this location. Here you can able to see there is one small symbol. This symbol is called as a connector symbol. So this connector, that MC4 connector, this is the MC4 connector, is used to connect the modules. Okay, so by default in a solar PV panel, the default the solar PV panel having a positive and negative cable of 1 meter. 1 meter default. This is the negative terminal. This is the positive terminal of the solar PV panel. By default, we are having 1 meter cable connection. Okay. So our inverter is located some 20 meters away. So for that, what we have to do, we have to use the MC4 connector, this connector. So then we have to extend the cable. There are solar PV cable, solar cables are available, especially for the solar PV system. For your information, the cables used in DC side of the solar system, we have to use only the cable which is meant for the solar applications. In the AC side, no problem, but in DC side, we have to use only solar rated cables only. So the cable also is available for 1000 voltage system, 4 square mm and 6 square mm. 1500 volt, again 4 square mm, 6 square mm, both are available in the market. So most of these cables are copper cables. Again, it's coated with tin. So what it means, the cable, normally you know, right? The cable conductor, on top of it, there will be an insulation. Okay. So for PV, there is a separate insulation is available. That insulation having the UV protection, because these solar PV systems are exposed to sun. There is the additional property called UV protection property added in those cables. Okay, and this will be the conductor, this will be the insulation. In short form, I mention as C and B. So these conductors are mostly made up of copper. That copper is coated with tin throughout the length. Suppose the cable is 10 meter for an example. So in the manufacturing itself, copper will be there. On top of it, there is a coating. That coating mostly with tin. Tin. Then copper. Inner will be copper. Then outer coating will be tin. Inner will be copper. Outer will be tin. In normally we can call this type of cable as tin coated copper cable. So why? Because that to achieve higher current carrying capacity. So compared to the copper, tin having the higher conductivity. Okay, so it can able to carry higher amount of current in a lesser cable size. So most of the cables are tin coated copper cables, right? So this will be the MC4 connector. The last one, this will be Y connector. Y connector, what it will do? So here we can able to connect one PV panel connection. This will be one panel connection. This will be the common output. So what it doing? It is paralleling to connection. For an example, this is the panel, two panels. I'm showing simplicity. Negative, positive, negative, positive. So the first one will comes here, second negative comes here. So the common negative will go from here. So similarly, one more Y connector will be there for positive. First one will come here, second panel positive comes here. Then this will be the common positive. So this common negative and positive will go to the inverter or the DC-DB in between. So this is for two panels. This is for three panels. This is for four panels. Sorry, four panels. This is the common paralleling connection. Okay, these connections are based on the requirement how you are designing your system. Then this is for five panels and this one for the six panel. So even if it is six means, so totally six panels will be there. Six panel negative will come here, negative Similarly, one more Y connector will be there. So here all the positives will come. So this will be a common negative and this will be a common positive. So this will go to the this common negative and common positive will go to the DC-DB or inverter, DC-DB or inverter, whatever it is. Okay. So this is the typical DC-DB. The common DC-DB. So here is this the SPD, surge protective device, and this will be the MCB. Okay. So where MCB we are using, so those locations we are not going to use the isolator, mostly isolator and fuse. So if fuse is there, then isolator to isolate. This will be fuse, this will be an isolator. Suppose in place of this, suppose if we are using a MCB means we are getting the combined function of protection as well as the isolation we can able to achieve through this MCB. Okay. So the input will come here. This is the negative, positive or negative. Similar to that, here positive, then this will be negative. This will go to the inverter. So from here, it will come from the panel. It will come from the panel, positive, common positive, negative. So this will go to the inverter. So here what we have established, this is the connection. So this is this point. This is this point actually. Okay. So we are getting the protection as well as the isolation here. So with the SPD, so we can able to see the SPD. What is SPD? SPD is a surge protective device. So whenever any electrical equipment exposed to sun, there is a higher chances of lightning. This is the, if you assume it's the top view of the rooftop, here we are installed the panel. Okay. Suppose if any lightning happen on this panel or if it is happen near to the system, there is a surge current or surge voltage that is get flowed through these circuits. Suppose if the lightning is hits in this panel, so it means that in this entire thing will get surge voltage and current. Okay, the system voltage normally 400 to 500 volt only. If lightning gets strike, then lightning voltage is very high. Okay, so mostly it will be in kilovolt and kilo ampere. Okay, so if the kilovolt and kilo ampere gets flowed through the circuit, what will happen? The circuit will get damage, equipment will get damaged, right? In order to prevent the equipments from the lightning, we are using the SPD, surge protective device. Okay. So this is there are two chances. One is the direct lightning stroke, that is especially lightning is hitting your equipment directly. Second one is the indirect lightning stroke. This will be direct and this will be indirect. So lightning hitting the nearby things. So from that there is an induction. This is the induction. So that will induce the over voltage in these electrical cables. So to prevent both, we are using this device called as SPD. Okay. So that SPD also, there are three types is there. 1, 2, 3, type 1, type 2, type 3. Type 3, I normally generally simply I write T1, T2, T3. Okay. So for the system where we are having the lightning arrestor. Suppose this is the top view, right? Here only our panels and all will be, we are installing in a on the rooftop. Suppose if you are having a lightning arrestor. like this. Inside view, if you see, we are having the panel up to this height. Okay, so we have to, this will be an lightning arrestor LA, lightning arrestor LA. So if we installed this one lightning arrestor, this will get covered. So for this lightning arrestor, there are some calculation is there, three types is there. So that coverage will gets like this. So it means that if any lightnings is coming in this coverage area, this method, this type of method is called as protective angle method. So there is some angle will be there. So based on that, we have to arrive how many number of lightning arrestor we need. So under this coverage area, if any lightning comes, this arrestor will capture, that will go to the ground. So this arrestor will connected to the ground. This will be an earth pit EP. So this will be ground. It will uh, divert the ground lightning to the ground. Okay. So for that application, we have to go with the type 2. If we are using the lightning arrestor, then normally we will use type 2. If you are not using a lightning arrestor, then we have to go with the type 3. Type 2 is for indirect type of protection. Indirect type of protection, type 2. For direct type of protection, it is type 3. There are some characteristics is there. So that characteristics normally we called as 8 bar 8 bar 20 microseconds, sorry, not millisecond, microsecond. So what it means, if any lightning happens, so this is the rise time and this will be the discharge time. So this time normally 8 and this will be 20. So this is the characteristics of the SPD of type 2. Similarly, for type 3, the direct stroke, this will not be a 8 bar 20-second type of characteristics, that having some different characteristics. Okay. Okay, so now came to the end of this presentation. So I will summarize. In this presentation, I have explained the stringing design. So how we have to do the stringing for a uh, inverter of 3.9 kilowatt, considering a 300 watt panel. So, and I have explained about AC versus DC ratio. So I given two example of 1 versus 1 DC ratio and 1 versus 1.5 DC ratio. So I have given two examples, and also I have calculated the stringing design. So based on the number of based on the wattage of the panel and rating of the inverter for one MPPT system, or when the number of MPPT system is 2 or 3. So so each MPPT is having the uniform rating. So if the panel, if the inverter is 9 kilowatt, if it is having 3 MPPT means, so each MPPT having 3 kilowatt. So we have to calculate the stringing design for the 3 kilowatt only. So there, so based on that, we have to arrive the number of panels in series as well as the parallel, right? So when we are doing the stringing design, that time we have to take care of the MPPT voltage rating of the inverter. That is the first criteria. Second criteria is the open circuit voltage VOC. Then third one is the P maximum PP current. So okay, these three criteria we have to see. And also I have explained about what is IV curve, what is PV curve. So from the nameplate detail, I populated the values in this IV and PV curve. Okay, and also I explained that the power rating of the PV plant for 24 hours load profile. So till during the night time there will be no sun, so there will be no power. So in the morning only sun will come. So when we are plotting the power rating, so it will be like this a curve. So it can able to deliver maximum power from typically 9 o'clock in, sorry, 10 o'clock in the morning to 3 p.m. in the evening. And also I explain about the series connection of the panels, and I have explained about the single panel connection through this MC4 connector, and multiple panel connection these through these Y connectors. Two panel connection, three panel connection, four panel connection, and 5 and 6 panel connection. Then I given some introduction about the surge protective device and the MCB. Yeah, that's all from my end for this presentation. So in the next one, I will take you to the building integrated photovoltaic system. So in the last time, I given some introduction about building integrated photovoltaic system. So I given some example in the next week. Yeah, if you have any doubt, you can unmute yourself and you can ask your doubts. So I hope everyone is clarified. So uh, I have uploaded all the record. Sorry, I have uploaded all the recordings uh, in a YouTube link. I already I shared it with you. So if you have any doubt, then you can go through the links. Actually, you can share it with your circle also, so that everyone will get familiarized with that. So I have one question. Do we need to have a panel of 1.5 times of the power of the inverter? Yes. For 1 versus 1.5 AC versus DC ratio, we should have the power rating of the PV panel is 1.5 times of the inverter, but the inverter rating is remain same only, but only the DC panel alone is 1.5 times. So that is to capture the energy in the less generation time, morning 6 o'clock to 10 o'clock, evening 3 o'clock to 6 o'clock. Yeah, so I shared uh, the YouTube link, and you can connect with me through the LinkedIn and this YouTube page. Uh, yeah, so that's all from my end.